What is probability? Probability is sort of an abstract concept. It feels more abstract than, say, a length of a rectangle or the height of a triangle. But in a way, probabilities do correspond to something physical out there. We'll get back to this later. So now let's talk about what probability is. Probability is a fraction. It's basically how many out of how many. So if your teacher is grumpy 2 days a week, then on any given day, the probability of your teacher being grumpy is 2 over 7. So a probability of an event or outcome, we denote probability with a capital P. And the probability is usually the number of success. That's a very optimistic term. By that, we mean the number of cases we're interested in. So in this case, the grumpiness of your teacher would be, and divided by the total number of possible outcomes. We're going to talk a lot about coins and rolling dice and cards. Right from the start, let me declare about gambling that it is a terrible addiction, and the first and probably the most important rule in gambling is that the house always wins. That's the same as you always lose. So don't gamble. We're going to talk about a lot of these things, but I just want you to understand I'm not encouraging you to get into gambling. That is not a good place to be. All right, that said, suppose we roll a die. Let's say the die is not rigged. That means that when we roll it, there is an equal likelihood that we get a 1 or a 2 or a 3 or a 4 or 5 or a 6. So they are equally likely events. So then what is the probability that we roll a 5? So when we are talking about a specific probability, this is the notation. And, well, rolling a 5, that would be 1 out of 6. So the probability of rolling a 5 is 1 over 6 or 1/6. Okay, let's see another example. What about the probability of rolling a number more than 4? So to roll more than 4, that would be 5 or 6, right? That is 2 out of the 6 or 1/3. So the probability of rolling a number more than 4 is 1/3. Now, what is the probability of rolling a 7? Well, the die doesn't have that side, right? It's numbered from 1 through 6, so the probability is 0 out of 6 or 0. And if you notice, this is the lowest we can go. We cannot have a negative probability, right? The number of successes, the number of possible outcomes, neither of them can be negative. So a probability is 0 or positive, and furthermore, it cannot get beyond 1. We cannot have 7 out of 3. So that means that probabilities, the value of probabilities range between 0 and 1. 0 would be never, and we can have a 1 too. What about rolling a number less than 10? Well, that would be 6 out of 6, right? So 1 means for sure, 0 means never happens, and probabilities cannot get below 0 or beyond 1. Okay, so let's talk about something that we call sample space. Let's say I'm playing the lottery. Did I mention don't gamble? It's not good for you. So let's say playing the lottery. And the question is, what is the probability that I get all the numbers right and win the biggest winning amount possible? Well, you can say that it's 1 out of 2. I either win or I don't win. That sounds a little fishy, doesn't it? When probabilities are defined, the number of possible cases have to have equal likelihood, which is here not the case at all, right? Me winning the lottery has a much less likelihood than me not winning the lottery, which is why you keep seeing me in class. So that is not a good sample space. Winning versus not winning. What is a good sample space is rolling a 1 or a 2, 3, 4, 5, or 6, because those events have equal likelihood. Okay, so I said previously that probabilities do correspond to something physically existing. And by that what I meant, it's called the rule of large numbers. Suppose we start to roll a die and we throw it 100 times, 1,000,000 times, millions and millions of times. When we roll a die, it's also sometimes called an experiment. So when we do a large number of experiments, the results usually approach the theoretical probabilities. So for example, if we roll a die, say 6 million times, then chances are that the number of 5s rolled is going to be in the neighborhood of 1 million. It's just about every 6th of the cases. The more experiment we perform, the more the number of success divided by the number of experiments will approach the theoretical probability. So in that sense, probabilities correspond to something physically existing. Alright, let's look at this other one. So this is our usual Venn diagram with our usual universal set, the integers from 1 through 10. And now we're gonna answer some probability questions about it. We randomly pull one number out of the 10. What is the probability that we're pulling a number that's in A? Well, remember, probability is how many out of how many. So what is the probability that we pull a number that's in A? That would happen if we pull a 2 or a 6 or an 8 or a 9. That's 4 out of the 10. So the probability is 2/5. This can very easily express as percentage too, right? If you multiply upstairs and downstairs by 10, that's 40%. Okay, what is the probability that we roll something that's in B? So now we basically need to count how many numbers can we pull that is in B. We find that 5 out of the 10 numbers are in B. So the probability is 5 out of 10, or 1/2. Okay. What about the probability that it's in neither A or B? What's that? You are right. It's 3 out of 10. So this is quite important. Sometimes we can rewrite the script a little bit to suit our purposes. For example, if we throw 2 dice, that might be a little bit more confusing than thinking, well, we're just going to throw 1 twice in a row. If we do that, how many outcomes are possible? Well, the first roll could be 1 or 2 or 3 or 4 or 5 or 6. That's 6 cases. And then completely independently, the second roll could be any of those 6. So there are 36 cases in the sample space. And we're going to write them down like ordered pairs. This would correspond to we rolled a 1 and then a 1. And that should be the same even if we roll 2 dice at the same time, but we sort of have to number them or color them to distinguish. So this is rolling a 1 and a 1. Now let's be organized and collect all the cases where first we roll a 1. I think you know where this is going. So if we roll a 1 first, the second roll could be, well, it could be a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And now we're going to rinse and repeat this column with starting with 2. So we're going to have 6 columns. The second column is with the first row being 2, then the first row being 3, 4, 5, and 6. So I'm going to write it down. You should probably make one and print out a bunch of them or make photocopies because you don't want to write this down a whole lot of times. Alright, so that is our nice sample space with 36 elements in it. And they are equally likely as long as the die is not rigged. So now let's have some probability questions. And maybe way down the road we're gonna look at complicated formulas, but at this point it's just how many out of how many. So let's say, what is the probability that the first number rolled is equal to the second roll? So equal numbers rolled. Well, we can just find them. It's this diagonal, right? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So that's 6 out of 36, or 1 over 6. And then we can sort of start wondering if there is a way to compute our way to that, especially when the answer is this simple. Let's count the successes. The first row could be anything it likes, that's 6. But then the second one has to be that same number, so that's just 6 outcomes. Okay. How about, what is the probability that the product of the two numbers rolled is 12? So again, we just have to count them. So 1 times anything is not going to give us 12. I think the first one is here, 2 and 6. And then 3 and 4, and 4 and 3, which you see they are 2 different cases. 2, 6, 3, 4, 4, 3, and 6, 2. So that is 4 out of 36, or 1 over 9. What is the probability that the sum of the two numbers rolled is odd? Again, we can just collect them, but when we start collecting, we can sort of have an idea. 1 plus 1 is 2, won't work. 1 and 2 will work. Don't work again, works again, doesn't work, works. So in the first column, we found 3 working. Is that the same here? 2, 1, yes. 2, 2, no. Yes, no, yes. So it looks like every column, exactly half of them will work. 3 plus 2. 3 plus 4, 3 plus 6. So it looks like every column has 3 of them, 6 columns, so that's 18 over 36, and that's just 1/2. Does that make sense? If we roll the first one, it could be anything say we rolled a 4. So for an odd sum, the next roll has to be either a 1 or a 3 or a 5. So that is 3 out of 6 for the second roll. The first roll could be anything it wants. So that's another way to get to the 1/2. Okay, what about the product being odd? When we multiply it, 1 times 1, that will work. 1, 2 doesn't, 3 works, 4 doesn't, 5 works, 6 doesn't. So we found 3 in the first column. It looks like it is similar to the previous one, but it's not going to stay similar for long, because look at the second column. 2 times anything is even. So this second column, none of the outcomes in that column are successes. And then again, half of the next column will work. Nothing from the column with starting with a roll of 4, and again half of these guys, and nothing from here. So we have 3 from here, 3 from here, and 3 from here. That's 9 out of 36, and that's 1/4. Well, does that make sense without counting? If we want the product to be odd, that means that both numbers have to be odd, right? So in the first roll, 3 out of the 6 will work, and in the second roll, 3 out of the 6 will work again. So that's how we get the 9 cases out of 36. Okay, let's look at some other probabilities. So we toss a coin twice. When we toss a coin, there are 2 outcomes. One of them is called head, which I get, and the other one is called tail. I have no idea why. We will not have to recognize which is which. So we toss a coin twice. What is the probability that both of them will be heads? So this is how we will represent an outcome. The first one is a heads, the second one is a head. And what's the probability of that? So this is a compact, nice little way of writing this question down. Let's see the sample space. So that's the equally likely events listed. Well, the first one can be a head, and the second one can be a head. Or the first one can be a head, and the second a tail. And now we're done with the ones that started with a head. So there is tail, head, and tail, tail. That's it. Again, we can think combinatorially. The first outcome, there are 2 options. For the second one, there are 2 options, completely independent of each other. So that's altogether 4 outcomes. And how many will work? Just 1. So the probability we're looking for is 1 out of 4, or 1/4. Thank you for watching.